Hello and welcome back. So sorry, this video is still not on dot product. Before that, I actually need to cover a few more concepts. So today in this video, I'm going to cover vector addition, scalar vector multiplication. So the first two actually are things we learned in secondary 4. Then I'm going to talk about collinearity and ratio theorem, which are things we pick up in H2 mathematics. So without further ado, now vector addition really is just an extension to resultant vectors. So let's put some numbers into our resultant vector example. So imagine if AB is 5, meaning 5i plus 5j. What that means is 5 units in the x direction and 5 units in the y direction. And BC is 8i, negative 6j. So how do you add two vectors together is basically you use the column vector form, add the numbers that are in the same direction, 5 and 8, that's 13, 5 plus negative 6, that's negative 1. That will be your resultant vector. Now a quick breakdown of how this works, so you can really see why we're adding up the individual components, because that is really just 5 plus 8 this way, and then plus 5 minus 6, that's a net of negative 1, so 13, negative 1 will actually get us to AC. The next idea I want to talk about is scalar multiplication. So we actually already seen this in the previous example question. So if I have some vector v, I can scale it up using a scalar. So I can scale it up twice by multiplying by a scalar number 2, or I can scale it up 3 times by multiplying by a 3. Now I can also turn it the other way around by multiplying with a negative 1, right? Scale it negatively, and negative 2, negative 3, so on and so forth. Collinearity, what is it? So from the diagram over here, you can see 4 points A, B, C, D. Now I can say that A, B, and C are collinear because I can draw one straight line and that passes through all 3 points. But A, B, and D are not collinear because there is no single straight line where I can draw that will pass through all 3 points at once. How do you check for collinearity? So if you're given sets of coordinates, what should you do? So first you should find the displacement between say 2 points A and B. Right? So this is what we call a displacement vector. Getting from A to B is some vector V. Then you want to check whether getting from B to C is also some scalar multiple. Of course, your scalar multiple could scale it upwards or scale it smaller or scale it in the opposite direction. That is all fine as long as it's a scalar multiple. A, B, C are collinear. So here's a quick summary on the test for collinearity. Number 1, you have to find displacement vectors, 2 of them, and prove that these 2 displacement vectors are parallel to each other. By parallel, we are really just saying they are scalar multiples of each other. Number 2, and this is rather important, the 2 displacement vectors must share one single point. If AB, the displacement vector, is parallel to BC, where they share the same point B, then this is sufficient to prove collinearity. But if say you have AB parallel to CD, this may not necessarily prove collinearity because AB and CD could be disjoint. So this is quite important in our collinearity test. Now the last concept I want to talk about in this video is ratio theorem. Say I have 3 points A, B, C, and they will form a triangle as long as they are not collinear. If I want to find a point D that is on BC, and D splits up BC in the ratio of lambda to mu, the vector AD will be lambda times of AC, mu times of AB. So there's some cross multiplication going on. Lambda times of AC, mu times of AB. Okay, that will be the numerator, and then divided by the ratio added together, lambda plus mu. Now the main problem students have with ratio theorem is identifying when to use it. My pro tip is to imagine ratio theorem to be a bow and arrow. So our previous points A, B, and C can be represented this way, right? Imagine that this is a triangle. And the thing we're really interested in is our arrow, AD. Okay, so remember there's a cross multiplication going on, lambda times AC, mu times AB, divided by the total, lambda plus mu. Now let's look at a practice question to reinforce all these concepts. Take some time to read this question. It's even better if you can take out a piece of paper and pencil and work through this before you look at the solutions. Welcome back. And as you can see, for this type of questions, you're given quite a bit of information. You know, you have some ijk vectors given over here. What I like to do for vectors question is, say if this is a foolscap, I like to reserve the top section over here for what I call planning, right? Our sketch diagrams, I'll write important information over here. Okay, so this is what I'll do. I'll do a quick sketch of say O, A, B, and C. Next, we're also given the position vectors of A, B, and C. Remember, the position vectors are just vectors, but the starting point is the origin, OA. So that's negative 3i, no j, and 4k. Alright. Another pro tip is, say as you're doing a solutions over here and somehow you need some information, it's always easier to refer back here on top and your info is given in column vector form. Great. Now I have all the information summarized at the top of my answer script. Let's look at part 1. Find a unit vector parallel to OA. Magnitude of a vector can be found using Pythagorean's theorem. That would be the square root of 25. I'll just take OA, negative 3, 0, 4, and divide it by 5. So this will be the answer for part 1. Now you can also give the answer to be this over here is the negative version of here. Why is this answer accepted? Because remember, if I were to multiply by negative 1, that's a scalar multiplication. What it does is it will take my vector and point it in the other direction. And remember that if I just want a unit vector that's parallel, it doesn't matter if I'm pointing towards OA or pointing away from OA. That is still parallel. Now in part 2, it says that a point P divides AC. So I've edited my diagram over here. AC is over here. There's a point P on AC such that it divides AC in the ratio 1:3. Find the position vector of P. So over here you should be able to see the bow and arrow. The bow is OAC, this big triangle over here. Now arrow is OP. So I can say by ratio theorem, cross multiplication going on, 1 times of OC, 3 times of OA. And all of this is divided by lambda plus mu, 1 plus 3, 4 over here. So I need to do this multiplication first. Now I can add the vectors together. And then dividing by 4, that will give us the answer, half negative 1, 3/4. And that's the answer for part 2. We need to prove that O, P, and B are collinear. So first of all, I need to show that the two displacement vectors are scalar multiples of each other. So maybe if we look at OB, if I were to factor out a negative 4 over here and 3/4, and you notice that half negative 1 3/4 actually is OP, so I can write this down as, and then you can clearly see that OB is a scalar multiple of OP. And if I were to read this correctly, actually is in the opposite direction of OP and 4 times the length. Right, so if this is OP, I need to go 4 times the length over here, but I do not have enough space, so I'm just going to draw maybe like that. As far as I can, B. So this is actually OB. Okay, and since OP and OB share a single point over here, I definitely know that they are collinear. So this is where I can make my conclusion. Therefore, that's part 3. Now moving on to part 4, it says that OBDC forms a parallelogram. So OBDC forms a parallelogram. Find the position vector of D. So position vector will mean that I need to start from O and go to D. So if I want to get from O to D, I can make use of resultant vectors. That is the same as OB plus BD. But what is BD? So you find that BD, because it's a parallelogram, it would have the same length and same direction as OC. So I could actually replace BD with OC. So OD is nothing but OB plus OC. So let's add that together. Adding the two vectors together, that will give us 9, 0, negative 12. And that is the answer for part 4. So I hope you found this video helpful and stick around. Hopefully the next one is dot product this time. And I'll catch you on the flip-flop.